Okay, so intermolecular forces. We talked about their existence. Now we're going to talk about exactly what they are. So how strong the intermolecular forces are depends on the structure of the particles involved. And the state of matter at a given temperature depends on the strength of those intermolecular forces. So the state of matter then depends on the structure of the particles. If you have strong forces, then you're going to have high melting and boiling points. If you have weak forces, low melting and boiling points. The intermolecular forces is what causes the particles to stick together at all. So if they're only held together very weakly, it doesn't take much thermal energy, much vibration and movement for them to break apart from each other. So then they boil at a lower temperature, they melt at a lower temperature. Intermolecular forces arise from charge attractions. These charges can be actual charges, as in ions. They can be partial charges, as in a dipole, or they can be temporary charges that we'll talk about. So we need to be acquainted with Coulomb's law. This is the full-out Coulomb's law. The energy, the potential energy of charged particles equals 1 over 4 pi epsilon 0 times Q1, Q2 over R. Now this part here is a constant, and we don't really need to pay much attention to that. Q1 and Q2 are going to be the charges on the particles. So if the charges are opposite, one's negative and one's positive, then this potential energy is negative. And negative potential energy is lower than positive potential energy. And whenever energy is lower, that's a favored thing. Everything goes to a lower elevation. Balls, rocks roll down hills, not up. So that's going to become, E is going to become more negative as Q1 and Q2 are larger and larger. So if you have a negative 1 and a positive 1 versus a negative 2 and a positive 2, the higher charge is going to have a stronger attraction. The other thing that affects the potential energy is R, and that's the distance between the particles. So if the particles are further apart, the force of attraction is less. And you can think of this in terms of magnetism. Think about magnets on the refrigerator, right? So you've got a weak magnet, and it'll maybe stick one piece of paper. You put 2 pieces of paper between the magnet and the refrigerator, and then the thing starts to slide. Have you had that happen? Or you get a really strong magnet, and it can hold a whole bunch of pages, right? The number of pages causes the separation to increase between the magnet and the refrigerator. And that reduces the force of attraction between them. If the magnet is stronger, then it can still hold the paper even at a larger distance. So the farther apart they are, the weaker the force is, and the higher the charge is, the stronger the force. Does that make sense? So if you can remember that, then you can reason out a lot of these other things that we're going to talk about. So bonding forces involve large charges at very close distances. So that's going to make them very strong. Bonding forces are covalent bonds and ionic bonds. Intermolecular forces are between molecules, and they are much weaker than bonds because they involve smaller charges and larger distances. So 2 things working against them. So in this illustration, we have 2 water molecules. And this covalent bond between oxygen and hydrogen, the distance here is 96 picometers. That's smaller than the distance between these neighboring molecules, which is 300 picometers. Okay, so this is a little over 3 times the distance, and so the force of attraction there cannot be as large. Does that make sense? So we're going to cover 4 different types of intermolecular forces. The first one is a dispersion force. It's got lots of other names. It's also called a London force, a London dispersion force, a van der Waals force, or an induced dipole force. The one your book uses is dispersion force. Dispersion forces are present in all molecules and all atoms. So let's look at how this could happen in an atom, because does an atom have a charge? No, atoms don't have charges. Ions do, but atoms don't. So if you have two atoms, they don't have charges. How can they be attracted to each other, right? Well, let's look at this. This is a helium atom. And so we've got 2 protons, 2 neutrons in the nucleus, and we have 2 electrons. Those electrons are in basically standing waves around the nucleus. But we can also think of electrons as particles. So here it's more convenient to think of them as particles. Because quantum mechanics says that if you observe them, then they're going to behave either as light or as particles, but they're not going to be both anymore. So if we were to take a picture of the atom, we would force the electrons to act as particles, and we could see where they were. We couldn't see how fast they were going or what direction, but we could see where they are. So I think of this as looking like a multiple exposure, well, not a multiple exposure, but taking a picture of a moving object, right, and it freezes it. So you take one picture, and here are the electrons. You take another picture, and here are the electrons. And they're kind of, on opposite sides. And then you take a third picture, and this time, they both happen to be on one side. So the atom is temporarily lopsided. We've got all the electrons over here. There's no electrons on this side. Here's our positive nucleus. So now we have a positive partial charge. It's not a full charge, but this side of the atom is slightly positive. This side is slightly negative. Does that make sense? So, I've told you I think of electrons as being a lot like little boys or children. So I have 6 children, and this reminds me of one time I walked into the living room, and all 6 of them were sitting on half of the couch. How often does that happen? I don't think it's ever happened since. That was a one-off. I took a picture because that was just so strange. They were looking at a picture on an iPad or something. It was hysterical. It doesn't happen very often, but it can happen. So anytime you've got, just sort of random things, it can be lopsided. Like sometimes in class during lab, right now you guys are spread out pretty evenly. Sometimes during lab, though, everybody's bunched up by the balances, right? Because you all need to weigh something. So the electrons can be bunched up, they can get lopsided, right? So when that happens, the atom is sort of in balance, and you've got a positive and a negative side. So we use the delta negative to indicate a partial negative charge. Delta positive indicates a partial positive charge. So if we've got one atom like this, it's going to affect a neighboring atom. So here's one atom that's lopsided. This partial positive charge on this atom is going to attract the electrons in a neighboring atom and induce a dipole in the next atom. So these electrons are attracted over here, and then we have an instantaneous dipole, a temporary dipole. So we've got this attraction between these 2 lopsided atoms. They don't stay that way very long. Like my kids didn't stay on the couch very long, like maybe a minute, and then they were off again. But it can happen. So this atom gets spontaneously lopsided. It induces a similar lopsidedness, is that a word, in this one, and that induces a dipole in the next one, and so we have this force of attraction between instantaneous dipoles in neighboring atoms. Another analogy I have for this is, think of this as a boat, and these are people on the boat. So maybe it's one of those blue and white cruises in the San Francisco Bay. So they got a bunch of people on deck, and you go on these cruises so you can see the sights, right? So people are all over the place looking at the sights, and now the boat gets near Alcatraz. and everybody's interested in Alcatraz, right? So everybody goes to that side of the boat, right? That's going to cause the boat to list. Hopefully just a little bit, because they were obeying the rules of how many people they can have on the boat. But the boat's going to tip just a smidge, right? So this boat is tipping. And then the neighboring boat is interested in that because, oh, look, everybody went to the other side. What's going on over there? That boat's maybe going to tip over. And so then everybody runs to the side of this boat. And then the next boat, right? I know, it's a stupid analogy. But you can visualize it, right? So that's what we call the dispersion force. It comes and it goes. So it's very weak. The magnitude, how strong that force is, depends on a couple of factors. It depends on how easily the electrons can move or polarize. How easily can those electrons get lopsided in response to an instantaneous dipole? If you have a larger electron cloud, I think of that as being a big and flabby atom, right? So the big flabby atom, this electron cloud, is really large, and so it can shift more easily than a small, tight electron cloud. So here's helium. He's just a slim, trim, tight little guy. His electron cloud doesn't shift around very much at all. He's only got 2 electrons, and he holds on to them pretty tightly. Here's xenon. Xenon's a big guy, right? And so you can't keep track of all these electrons at all the time. It's a little bit like, a small family and a large family. I often do not know exactly where my children are because it's just not possible. They're just, kind of all over the place. So this electron cloud is more easily shifted. You can induce a dipole in this electron cloud easier than you can in something that's small. And we can have evidence of the strength of these intermolecular forces by looking at the boiling points. So the boiling point of helium is 4.2 Kelvin. That's really low. And as we increase in mass and increase in the size of the atom, the boiling point goes up. Higher boiling point means that those dispersion forces are weaker. So the forces are weaker in xenon with a boiling point of 165 than they are in helium. So as the molar mass increases, as the size increases, dispersion force generally increases in strength. Does that make sense? The shape of the molecule also plays a part. This happens in atoms, but it also happens in molecules. So if we look at these two molecules have exactly the same mass because they are structural isomers. So they both have the same chemical formula, but they're arranged differently. So this is normal pentane. So the carbons are in a chain, and this is what's called neopentane, where all of the carbons are attached to one carbon in the middle. So this molecule is more spherical in shape, and this is more linear in shape. So these two molecules have a larger area where they can interact than these two spherical ones. So if you think of these as objects covered in Velcro, two spheres covered in Velcro can only touch at a very small point. And so they're not going to stick together very well at all, right? The Velcro is going to hold them together in a very weak way. It's easy to pull them apart. If you have a larger surface area, the Velcro is going to stick tighter. So, we've got Velcro on your shoes or your jacket or something, and you can pull it open pretty easily, right? Have you seen those bounce house things where you put on this Velcro suit and you bounce against the wall and you stick, right? How is it that the Velcro that won't stay closed on your shoe can hold someone's body against a wall? It's more surface area, right? You've got your body's surface area. So more surface area, stronger force of attraction. So these molecules are going to be able to stick together stronger than these spherical ones. So here we can compare strength of dispersion forces because we're looking at boiling points. So higher boiling point means weaker, higher boiling point is stronger dispersion force. So here we've got normal pentane, and here what normal means is that the carbons are all just in a straight chain. So we've got pentane, hexane, heptane, octane, and nonane. So these are similar molecules, carbons and hydrogens, but they're getting longer and longer. So the molar mass is increasing, and the surface area, this one being long, it has more surface area that it can be attracted to other molecules than pentane does, because pentane is short. And so we see that the boiling point goes up with molar mass and increasing length of the molecule. Any questions? So that's the first one. Everything has dispersion forces. The second one is a dipole-dipole force. Dipole-dipole forces are found in all polar molecules because this is an interaction between permanent dipoles. So polar molecules have permanent dipoles. They always have a positive and a negative end. Because these dipoles are always present, dipole-dipole forces are going to be stronger. Because dispersion forces come and go, come and go, come and go, and so they're very weak. A dipole-dipole force is always present, and so it's stronger. So here we have space-filling model and electrostatic potential map of a molecule that's polar. So here the oxygen end of this molecule is more negative, the hydrogen end is more positive. So the negative end of one molecule is attracted to the positive end of a neighboring molecule. Here we see higher electron density here and lower electron density there. So there's an attraction, and that attraction is always present. So polar molecules have dispersion forces because everything has dispersion forces. They also have dipole-dipole forces. So polar molecules, in general, have higher melting and boiling points than nonpolar molecules. You have to compare things of similar size, though. So here we're going to compare formaldehyde and ethane. There are the formulas. Their molar masses are very close. So we can't say that any differences in boiling points are due to larger electron cloud that's more easily polarizable. This one is polar, and this one is nonpolar. And so what we see is the boiling point for formaldehyde is much higher than for ethane. Minus 19 versus minus 88. And the melting point, minus 92 compared to minus 172. Lower boiling point, lower melting point means that the attractive forces, the intermolecular forces, are weaker. So you think of these, you can think of intermolecular forces as stick-togetherness, right? So how sticky to each other are they? If they're very sticky, then it takes a lot more energy for them to break away, right? And if they're not very sticky, they can just slide around very easily. And the amount of movement they have is related to their temperature. Any questions? So here's a graph comparing difference in boiling point based on dipole moment of these different molecules. So we've got some molecules here that are very similar in molar mass. So we've taken that out of the question. And here we're looking at dipole moment, down here, dipole moment. So as these become increasingly polar, from 0.08 up to 3.92, we see that the boiling point increases as the molecules become more polar. Polarity of molecules is very important in determining miscibility. So that's a word we don't use in everyday life. Miscibility, you can kind of think of that as mixability. That's not a real word, but it would make sense to you. Mixability, the ability to mix, right? Miscibility is the ability of liquids to mix without separating. So we know from experience that if we mix oil and water, we can shake them up, but we cannot get them to mix. If you take something like ethanol and water, alcohol and water, those are going to mix very nicely. They are miscible. They will not separate out. They will stay mixed. And so what the little catchphrase we use is like dissolves like. So if the two liquids we're looking at are both polar, they will probably mix. They are probably miscible. If they are both nonpolar, they're probably miscible. If you have one polar and one nonpolar, they're not going to mix. Because the forces of attraction here between the molecules of water include dipole-dipole forces, and the pentane does not have dipole-dipole forces. So the water molecules are very attracted to each other, and they like each other so much that they push out the pentane. They exclude it, so it can't mix in. Any questions? Okay, so this is a type of question that we should be able to answer. Which molecules have dipole-dipole forces? So what does a molecule have to have or be to have dipole-dipole forces? It needs to be polar. So we're looking for which of these is polar. So this one, this is CI4. I put the name there because sometimes it's misinterpreted as CL4, which doesn't make any sense at all. But so refresher on how to predict if a molecule is polar. This works most of the time. Draw the Lewis structure and look at the number of lone pairs on the central atom and the number or the types of atoms bonded to the central atom. So carbon tetraiodide, I'll just finish it out because I don't want to be accused of doing an incorrect Lewis structure. That would be just horrible, wouldn't it? So that's the full Lewis structure for carbon tetraiodide. My shortcut is two things have to be true for it to be nonpolar. No lone pairs in the central atom, and all the atoms bonded to the central atom are either the same element or they have the same electronegativity. So does this one have any lone pairs on the central atom? No. Are all of the atoms bonded to the central atom the same? Yes. Is this molecule polar? No, it's nonpolar. Nonpolar molecules are symmetrical. Polar molecules are lopsided in some way. So that one's nonpolar. Does it have dipole-dipole forces? No. So this is a no. How about CH3Cl? Well, carbon in the middle, hydrogen, hydrogen, chlorine, hydrogen, and then chlorine has some lone pairs. Is that polar? Yeah. There aren't any lone pairs on the carbon. These four bonds are distributed in a tetrahedral shape, but this one is different, right? So the molecule's lopsided. This is a polar molecule. So does it have dipole-dipole forces? Yep. All polar molecules have dipole-dipole forces. Let's look at HCl. So this is a diatomic molecule, just two atoms. There's only the one bond. So we can't use those shortcut rules because there's no central atom. But all we have to do is identify, is this only bond polar or nonpolar? It's polar. How do you decide that? Well, most of the time, if those are two different elements, it's going to be polar. There are some exceptions, but I will not trick you with those on an exam. So yes, this molecule has dipole-dipole forces. Any questions? So you see how things are building up here? If you can't do a Lewis structure, you can't predict whether it's polar or not, and then you can't predict what kind of intermolecular forces it has. So if you're a little behind, go back to drawing Lewis structures and catch up. You can skip molecular orbital theory. It's not really going to affect much of anything else. I'm required to tell you about it. Okay, so we've done dispersion forces, dipole-dipole forces, and now we're going to talk about hydrogen bonding. So I think of hydrogen bonding as being super dipole-dipole force, right? Dipole-dipole force on steroids, just extra. It's the same idea as dipole-dipole forces, it's just extra strong. It's extra strong because it is found in polar molecules where you have hydrogen bonded to a very electronegative element, such as fluorine, oxygen, or nitrogen. These are small and highly electronegative. So these are extrapolar molecules. It's called hydrogen bonding because hydrogen is involved. It's easily confused with a covalent bond between hydrogen and something else. That's not what it is. It's an intermolecular force. Okay, so how do we remember that it's fluorine, oxygen, or nitrogen? Oops. So, have you seen or at least heard of the movie E.T.? Okay, what did E.T. say? E.T. phone home, right? And he'd point at this, E.T. phone home. Phone home. Okay, you like that? I'm pretty proud of that one. So fluorine, oxygen, or nitrogen, yeah, it's spelled wrong, that's okay. Phone connected to hydrogen. Okay? So if you have a polar molecule where you have hydrogen bonded directly to fluorine, to oxygen, or to nitrogen, that molecule is going to have hydrogen bonding.
And does that mean that it's going to have dipole-dipole?
Yes, it's going to have dipole-dipole forces because it's polar, and it has dispersion forces because everything has dispersion forces. Excellent point. So we look at this. This might be something like HF, where we've got a hydrogen and a fluorine. So the hydrogen end is positive, the fluorine end is negative, and so we have this force of attraction between adjacent molecules. It's not the bond between hydrogen and this other atom. The covalent bond is not the hydrogen bond. The hydrogen bond is the extra strong dipole-dipole force present in these molecules. So here we can look at ethanol. Ethanol has oxygen directly bonded to hydrogen. It's a polar molecule because this oxygen has lone pairs. This bit over here with the carbons and the hydrogens, carbon and hydrogen is that one exception I want you to remember where you have two different elements, but those bonds are considered nonpolar. So this part's nonpolar, but this part is definitely polar. So this hydrogen has a partial positive charge. This oxygen has a partial negative charge, and so we have this force of attraction. What makes this different than a dipole-dipole force is these partial charges are larger, and oxygen, nitrogen, and fluorine are small, right? They're in the second period, and they're on the right side of the second period even. They are among the smallest atoms. Small atoms are able to get closer to each other. So because this oxygen is small, it can get close to the hydrogen. And distance is a factor in the strength of the intermolecular force. Water also has hydrogen bonds. Water is a bent-shaped molecule because of the lone pairs on the oxygen. So we've got attractive forces between positive hydrogens and negative oxygens. And here's with the space-filling model. Any questions? So, important points. Hydrogen bonds are between molecules. Chemical bonds are within a molecule. Those are between individual atoms within a molecule. This point should probably be up here. This is referring to hydrogen bonds. Hydrogen bonds are only about 2 to 5% as strong as a covalent bond. So they're much weaker, but they're just bigger than the dipole-dipole forces. So because hydrogen bonds are stronger, things that have hydrogen bonds have higher melting and boiling points. So here we can compare ethanol and dimethyl ether. Dimethyl ether is a polar molecule. If you look at the Lewis structure, or sort of a shortcut Lewis structure, the oxygen has 2 lone pairs on it. And so it's going to have a bent shape, and the oxygen will be slightly negative, and the CH3 sides will be slightly positive. Does this molecule have phone home in it? Does it have hydrogen bonded to oxygen, nitrogen, or fluorine? It has oxygen and it has hydrogen, but are they bonded to each other? No, they're not. So the hydrogens here are bonded to carbon, not to the oxygen. That might be confusing how I drew it. So let's try that again. So oxygen, carbon, the hydrogens are on the carbons. I know, I sometimes forget that you guys aren't familiar with the way organic chemists draw their molecules. When you see, that was a C. When a chemist does CH3, that means the 3 hydrogens are bonded to the carbon, and then the carbon is bonded to something else, but never the hydrogens, because hydrogens can only be bonded to one thing at a time. Right? So there's no hydrogen-oxygen bond here. So this is a polar molecule, but it doesn't have hydrogen bonding. This one does have hydrogen bonding. So this one would be got OH over here, and C and C. So that's the, there it is. That's the Lewis structure for ethanol. We have an oxygen-hydrogen bond. This guy has lone pairs on it. It's an asymmetrical molecule, it's polar, and has hydrogen bond. Then we look over here at the boiling points and the melting points. Their molar masses are exactly the same because they're the same number of carbons and hydrogens and oxygens, just put together differently. Ethanol has a boiling point of 78 degrees Celsius, and dimethyl ether boils at minus 22. So if you look at room temperature, dimethyl ether is a gas, ethanol is a liquid, because the forces of attraction are stronger and they can hold them together at higher temperatures. Any questions? Water is actually a very strange substance. Here we've got a graph showing boiling point versus molar mass, and we're looking at, this is one of those ones where they mislabeled. This is not group 4A, and that's not group 6A. They've got them backwards. That's 6A, and this is 4A. So carbons in group 4A, silicon, germanium, tin. These are going to form compounds where they bond to 4 hydrogens. We see that there's a trend of increasing boiling point as the molar mass gets larger. And that makes sense because that's what dispersion forces do. Larger molecule, stronger forces due to the flabbiness of the electron cloud. But these are nonpolar molecules because they're symmetrical. And then here we have group 6A. So here's sulfur, selenium, tellurium, and there's oxygen. These form compounds where they bond to two hydrogens. These are polar, and so overall their boiling points are higher than the group 4A, which are nonpolar. And we see this trend of increasing boiling point with increasing molar mass, but somebody's sticking out like a sore thumb, and that's water. If you look at the general trend, looks like a pretty nice line, and you would expect water to be down here, minus 80 or so degrees Celsius. That's really cold. But the actual boiling point of water is plus 100 degrees. So water has much stronger intermolecular forces than similar compounds involving sulfur, selenium, and tellurium. And the difference is that water does hydrogen bonding. Sulfur can't do hydrogen bonding. It's not small enough and it's not electronegative enough. So this is hydrogen bonding, and so that causes the boiling point of water to be much higher than it would be otherwise. And that's a good thing, because if hydrogen bonding didn't exist, all the water on our planet would be in the gas state. That would be a very different place, wouldn't it? All the water in your body would be in the gas state. That could give you nightmares thinking about that. Okay, so we should be able to answer a question like this. Which has the higher boiling point, HF or HCl? And then the dreaded question, why? Because if there wasn't why, you could just guess and you'd have a 50% chance of being correct. So what do we do here? Well, I'm going to draw Lewis structures for these guys. They are similar molecules, right? If you're asked to compare boiling points, you're going to look at what types of intermolecular forces do these compounds have, and that involves identifying, are they polar or not? So are these molecules polar? Yeah. They're both two different elements, so we can assume they're polar. So they're both polar. So do they both have dispersion forces? Yeah. Because everything has dispersion forces. So both have dispersion forces. Do they both have dipole-dipole forces? Yes, because they're both polar. So far, they're very similar. What about hydrogen bonding? HF has hydrogen bonding. HCl does not. So this has hydrogen bonding, and this one does not. Dispersion forces are the weakest. Dipole-dipole forces are the next strongest. Hydrogen bonding is the strongest. So HF has the strongest intermolecular forces. It's the most stick-togethery. So will its boiling point be higher or lower than HCl? Be higher. So HF has a higher boiling point. Because it has hydrogen bonding, its intermolecular forces are stronger. Yeah?
So anything bonded, not talking about HF, but anything bonded with hydrogen has a higher boiling point?
No, not everything bonded with hydrogen has a higher boiling point. Because you can have hydrogen in nonpolar molecules. So that's got hydrogen, but this does not have hydrogen bonding. It has bonds between carbon and hydrogen, but those are covalent bonds. And the unfortunate name of hydrogen bonding suggests covalent bonds, but that's not what it is. The hydrogen bond is a super dipole-dipole force. So it's attraction between two different molecules, and the key there is F, O, or N directly bonded to hydrogen. Now, is the strength of the dispersion force different in these two? The biggest, or a significant thing that affects strength of dispersion forces is the size, right? Which is bigger, HF or HCl? HCl is larger. So this is going to have stronger dispersion forces, but here, because we have this difference in hydrogen bonding, that is completely going to outweigh any dispersion force differences. Because hydrogen bonding is the big guy, the strongest. Any questions? The fourth one I take issue with because I would say this is not technically an intermolecular force. The ion-dipole force is a force between ions and a polar molecule. So, but they include it, so we'll talk about it. When you have an ionic compound mixed with a polar compound, something like salt in water. So sodium chloride dissolved in water, you've got the sodium ions, you've got the chloride ions. There's an attraction between the polar water molecules and the chloride ions. The positive end of water is attracted to the negative ion. The positive, backwards again. The negative end of water is attracted to the positive sodium ion. That's the ion-dipole force. That is stronger than hydrogen bonding, but it's never used in comparing boiling points because this is not within a compound. This is between two different compounds, and it's between ions and molecules. But this force of attraction is responsible for the ability of ionic substances to form solutions with water. This is why things can dissolve in water. So here's a table from your textbook summarizing the intermolecular forces. So they're listed in order of increasing strength, and you should know the order here. It's giving you strength with some numbers here. I don't expect you to know that. You should know what kind of things have these different forces. And you should be able to draw a picture of some sort or explain in words what this is. The important distinction is that the bond, like hydrogen bonding, is between hydrogen on one molecule and oxygen on another. It's not a covalent bond. It's just electrostatic attractions. So hydrogen bonding is important in a lot of different things. Your body has a lot of molecules that are hydrogen bonded, and it's really critical to the existence of life. So you're probably familiar with DNA. You understand that living organisms have DNA. DNA is composed of two strands, two long molecules twisted together. There's a sugar phosphate backbone. That's the chain, and then it has these bases that are hanging off, sort of like charms on a charm bracelet. These bases can hydrogen bond with each other. So there's 4 bases, and I'm not going to expect you to remember these. This is just to show you that hydrogen bonding is important. Thymine, adenine, cytosine, and guanine. So thymine and adenine, thymine has an oxygen here that can hydrogen bond with the hydrogen bonded to nitrogen on the adenine. And then there's this nitrogen-hydrogen bond here, and we can get hydrogen bonding between that hydrogen and a nitrogen on the adenine. So these 2 bases can form 2 hydrogen bonds with each other. And so it's kind of like magnets. They're just going to kind of click together, very attracted to each other. The other 2 bases can form 3 bonds, 3 hydrogen bonds. And so cytosine is always going to match up with guanine. It's not going to match up with adenine or with thymine. So this pair has 2, this one has 3 hydrogen bonds. So when your DNA replicates, the 2 original strands are separated, and new bases are brought in that match up, and then they're connected with the sugar phosphate backbone. If you're interested in how that occurs, you might want to look into biochemistry. It's really pretty cool. So originally you have AT and AT and CG. There's a pattern here, and the pattern of those base pairs is what determines what color your eyes are and how tall you are and all kinds of other things. You need to replicate your DNA, and so the two strands come apart, and the new strand can be formed because only cytosine will bond to the guanine, and only tyrosine will bond to the adenine. Sorry, it's not tyrosine, it's thymine. But they're going to match up, and so the new strand is going to match the original strand, and so you end up with two identical strands of DNA. And there are different checks and things that go in there and fix anything that happened to go wrong. But any questions about DNA?